New chapter, the mole concept. We finally made it. We arrived at moles. So to talk about moles, we're first going to talk about donuts. Donuts, as you may know, are a frequent feature of big grab-and-go breakfast settings, like office meetings, seminars, church group meetings. And typical donut orders are likely to be less than 1 or 2 boxes, depending on the size of the group, of course. Some groups you might end up ordering a lot of boxes of donuts. Now let's say you're hosting a large party and you have to pick up 250 donuts from a bakery. If you arrive at the donut shop and they've got all of your donuts out in boxes, that's going to be a lot of boxes of donuts. And if you were to go and count every single one of those donuts individually to make sure that they were all full, that would probably take you quite a bit of time. You'd have to unstack, restack, open, close, do a lot of counting. It would be a lot faster if instead you just knew how many donuts were in each box. So in this picture, for example, all right, we've got 3 rows of 4 donuts. We've got 12 donuts. In one box, or a dozen donuts in a box. So we could figure out what a multiple of 12 is that's close to 250. We could even just do straight up math, right? Use this as a conversion factor, 12 donuts in one box. If we've got 250 donuts, we divide by 12. And we would get 20 boxes with a remainder of 10. So a number, I don't want to pull my calculator out for this one. 20 boxes plus 10 donuts, we would expect to see 21 boxes. And that wouldn't take very long. They'd probably be stacked up in rows. We could do some quick multiplication, but counting up to 21 wouldn't take you very long. And if you're lucky, they would probably just throw in some extra donuts for such a large order. And I just did that example because I forgot that I put an example slide in. Okay, so if we're counting things like donuts, if we're counting smaller quantities relative to the scope of things that we talk about in chemistry, a dozen, like in a box of donuts, is a great number. If you start to scale that up to larger things, like feet and a mile, 5,280 feet, sure, you could go out and put down 1-foot marks, but it would be much easier if you just magically had a 1-mile long stick. I don't know where you'd store it. But it's more convenient to use a larger measuring tool rather than these small measuring tools. So a dozen's great for donuts, but when we're talking about atoms, atoms are so unbelievably small that a dozen doesn't even make it any more convenient for us. And so in chemistry, our version of a dozen is called the mole. And the mole is an absurdly large number of atoms, or formula units, or molecules, or whatever the thing that we're talking about is. So 1 mole, the full spelling being M-O-L-E, we chop off the E when we use it as a unit to save us tons of time. You'll find that that's a common theme with chemistry. We chop off one thing, or we very minorly reduce the amount of work that we have to do. So 1 mole is equal to 6.022 times 10 raised to the 23rd power. And this is especially a place where scientific notation is super nice. Because if we didn't have scientific notation to use to put that number into our calculator, it would look like this. And that just wouldn't be very fun to write out on a piece of paper. much less to put into our calculator if it even let us put that number in. So that's the scale of how many molecules or atoms or formula units, how many singular pieces are in a mole. And this number is called Avogadro's number, named after Amedeo Avogadro. You'll also probably hear me call it Avogadro's number or Avocado's number, because I think that both of those are funny. You will generally be given Avogadro's number. Sometimes it'll be given this symbol, capital N with a subscript of capital A, the number of Avogadro. The way that we use this is similar to the way that we used a dozen. So swap out dozen for mole, and swap out donuts, our singular unit, our smallest piece, for atoms. So let's say that we've got a mind-bogglingly large number of 9.5 times 10 to the 25 atoms, and we want to convert that to the much more palatable, but not as palatable as donuts, moles. We set up our given number, and we put Avogadro's number as our conversion factor. One of the nice things about Avogadro's number being so big is that you're either going to make something ridiculous or you're going to make it less ridiculous. So 9.5 times 10 to the 25 is a ridiculous number. This is a very obscenely large number. We don't want to make this more ridiculous. There's almost never going to be a situation where you're going to make that more ridiculous. We want to make it less ridiculous. So we're going to put Avogadro's number in the denominator. We're also doing it like we would with any of our other conversion factors that we've used in the past. But that can be one way that you could check if you set it up correctly. So atoms cancels atoms, and then we get the very fun job of putting this into our calculator. So 9.5 times 10 to the 25 power, divide that by 6.022 times 10 to the 23rd power, and you should get a number that's around 157.75 moles. For significant figures, we would treat this like two significant figures. So there's our sig figs answer. If you have a calculator with you, I highly recommend that you actually try plugging this in and see that you get the correct answer. Some of the calculations that we do in this class are very easy to mess up, so it's a good idea to test it in a low-stakes setting before we use it in a high-stakes setting like an exam. So a couple of ways that you can put this into your calculator. There's the way that you probably know how to do it, where it would look like this. and you would get the correct answer. Parentheses is sometimes optional, but you're never going to put parentheses in and have it mess you up unless you put it in wrong. So even if we don't need the parentheses there, doesn't hurt for us to put those there just to make sure that this all works as planned. It shouldn't affect anything here though. At least on the first number. The second number might screw things up. I'll show you another way to do it coming up here on this next example. The element carbon, that's C, number 12 on the periodic table, exists in two primary forms: graphite, like in pencils, the lead in pencils, and diamond. How many moles of carbon atoms is 4.72 times 10 to the 24 atoms of carbon? So we are given a large number of atoms of carbon. And we want to convert this to moles also of carbon. We can do this in one step thanks to Avogadro's number. 4.72 times 10 to the 24, and we have two units. Our first unit is atoms. Our second unit is carbon. We can just write atoms and then the symbol for carbon, C. And we want to make this ridiculous number less ridiculous. So when we apply our Avogadro's number, we're going to put the big number on the bottom. And that will carry with it units of atoms, since that's what we're counting. So the atoms cancel, and the units that come through are moles and carbon. The other way that you can put this into your calculator, depending on the calculator you have, is there's the dolphin noise key on your calculator. It's two capital E's right next to each other. If you sound that out repeatedly, kind of sounds like a dolphin. So this little capital E, not to be confused with lowercase e, because those are different. This capital E that's small means 10 raised to the power of, and then what follows it. That's what it's telling your calculator. So we can write 4.72 little capital E 24 divided by 6.022 small capital E 23. We do not need parentheses here. And that will get us the correct answer as well. So if you have that dolphin noise key, you are welcome to use that. That's what I use. It saves you a couple of button presses. If you don't want to use it, you'd rather use 10 raised to the power, you're also welcome to do that. There's no difference functionally. The answer we get is 7.84 moles carbon. So from a very ridiculous 10 to the 24 to a much less ridiculous 7.84. Questions about using our new favorite number? Great. Another thing that we can do, now that we have some knowledge of chemical names and formulas, is we could calculate the number of hydrogen atoms in two water molecules. This would be possibly a setup step or a follow-up step using with Avogadro's number. So water has the chemical formula of H2O. This means we've got two hydrogens the omitted subscript of 1 on the oxygen, trailing the oxygen, means that we've got 1 oxygen. So 2 hydrogens in every H2O. We can convert the chemical part. This is our first, I think, chemical conversion. So we're converting the chemical unit. We will be doing this a lot more in the sort of nearish future. So if we start with 2 H2O, for every 1 H2O, there's 2 H's. So we constructed that conversion factor based on the chemical formula. Pretty simple math. We can even count it out with these nice renderings from my hero, Ben Mills. The 4 white dots here, 4 hydrogen atoms. Any questions about doing that? Great. What if we have 1.5 moles of water molecules? That's a lot more water molecules. Water still has the formula H2O. 1 molecule of H2O still has 2 hydrogen atoms. And so we can solve the problem now with 2 steps. So the first step that we might use is to convert moles to molecules. Moles H2O to molecules H2O. That's the first step that we did here. Then our second step would be converting to atoms H2. So our first step was convert the quantity, moles to molecules. Our second step, we converted the chemical. You could do these steps in the other order if you wanted to. It doesn't make a difference. Notice that we also swapped from molecules to atoms. That's sort of a pedantic thing. It's just we're counting the smallest unit. In the case of H2O, H2O is a molecular compound, so its smallest unit is molecules. Atoms, on the other hand, are the smallest unit of an element, hydrogen. And then we would just multiply everything across the top to get to our atoms of hydrogen. So just combining the 2 steps that we went over individually. Other important numbers that we'll need to use include the molar mass. The molar mass is a massively important unit for chemistry. It's the mass of 1 mole. Molar as in pertaining to moles, and mass as in mass. So it's the mass of a mole. And it's numerically equivalent to the atomic mass in grams. The atomic mass we can get from the periodic table. And it's that number that lives underneath our element symbol. In the case of the periodic table we have in class, we've got pretty long numbers. On your yellow sheet, there's some other numbers that are on there. These are the ones specifically that are always going to be like above 4 except for hydrogen. So like for helium, 4.00260 or whatever it says there. magnesium Mg 24.3 and some change. Those are the atomic masses. And those have the aptly named atomic mass unit for their unit. AMUs is not grams per mole, but the numbers are the same for grams per mole and AMU. Let's make that an arrow. So anywhere you see AMU, you can switch that out for grams per mole. For some of them, you'll notice that it's got a whole number. It's got an integer value, and it's in parentheses. Yeah, those are parentheses. That's because we've only made that one version, so there's not like multiple isotopes that we're averaging together. Most of those also don't exist right now. All right, calculating molar mass is similar in a way to counting money. It's different because your money doesn't come all glued together, whereas molar mass, all the pieces come glued together. But the way that we calculate a molar mass is based on counting up each of the individual components. So each element has a molar mass value. We can get those from the periodic table, from your yellow sheet, from an app on your phone, from Google, from the periodic table that you keep in your wallet, wherever you want. Then we multiply the number of atoms by its molar mass. And then we can add up the totals for each of those elements. And so your calculations might end up looking something like I've drawn up in this table. So for sodium carbonate, Na2CO3, we've got three different elements. We've got sodium, and we have two of those. We've got carbon, we've only got one of those, and we also have three oxygens. We find the molar masses, or have them memorized, probably from repetition. We multiply the molar masses by the number of atoms. So sodium, we had 2 times the molar mass of sodium to give us a total for sodium of 45.980 grams per mole. We do the same process for carbon and for oxygen, add all of those numbers up, and we get a relatively light 105.988 grams per mole. You are welcome to just ignore significant figures for doing molar mass calculations. It shouldn't be an issue because we usually have at least 4 significant figures. A lot of the time our measurements are not going to have much more than that. They'll be limited in some other way. If you're concerned that your numbers are not good enough, you can always find better molar mass numbers, like on the periodic table in the class or asking Google. There's always more decimals to be found somewhere. I keep a few extra decimals in my desk at work, just in case I need them for sig figs. All right, so that's how you do it, but let's see it in action, because that's more interesting. So calcium nitrate, CaNO32, is used as a component in fertilizer. Let's determine together the molar mass of calcium nitrate. Fortunately, we are given the formula, so we don't have to rely on our nomenclature skills. That is something that I may call upon you to do at some point. I will just tell you it's calcium nitrate, and you'll come up with the formula. Expect that in the future. So we're given the formula, and we are looking for the molar mass of the calcium nitrate. So let's count out how many of each element we have. Our first element, calcium, implied subscript of 1, just 1 calcium. Then we get to our NO3 groups. We've got NO3, and it's in parentheses, and there's a 2, so that 2 is going to distribute to the subscripts of the things inside when we're counting up the total amount. So for our nitrogen, we actually have 2 times the written subscript, or implied subscript of 1, so we've got a total of 2. And then oxygen, we've got 2 nitrates. Each nitrate has 3 oxygens, and so we've got a total of 6 oxygens. So those are the counts. And then we need to get our molar mass values from the periodic table. This is where it's helpful to have some proficiency in finding where these things are located. You'll get better at this the more that you do it. So 40.074 for nitrogen, 14.0067 for oxygen, 15.9994. And those all have grams per mole on them. And then we multiply these numbers to get some subtotals for each of our elements. You don't necessarily have to do all of these as individual steps. If you don't have a calculator that can put in a lot of things, you might want to keep track of it as you go. Okay, so our subtotals are there, and then we add them all together. And we get a whopping 164.0878 grams per mole. If you use the yellow sheet instead of the periodic table in class, like I'm expecting a lot of you did, your answer is probably a little different. It's not the end of the world. It should be very close. Questions about what we have done here? This is one of the key skills for Gen Chem. We'll be using this for the rest of the class. If you want more practice with calculating molar masses, I'm sure that all of you are just wondering, how can we practice this more on our free time? We'd love to do more calculations. You take your book, your chemistry book, just flip through it, find a chemical formula, calculate the molar mass, and then ask Google what the molar mass of that chemical formula was. And if you're really close, nice, you nailed it. Or you could probably just find, I'm sure there's a tool somewhere out there that will just tell you a random chemical name or chemical formula, and then you just calculate and compare to like Wikipedia or what Google tells you. So there's lots of practice out there to be had. The reason that we're learning molar mass is because it's our conversion between moles and mass. It's got units of grams over moles, and if you train your brain, anytime that you see a unit that's got or a number that's got 2 units in it, or a quantity that has 2 units in it, you can train your brain to see that that is what the units you can convert between are, even if you've never seen it before. So we can convert grams and moles. It's already set up like a conversion factor, and the number part stays with the grams. There's an implied 1 that stays with the moles. So we can use this to move between moles and mass. For example, we want to know what the mass is of 3 moles of these forbidden marshmallows, calcium carbonate pellets. Our molar mass is 100.09 grams per mole. So the thing we're given, 3 moles. My rule of thumb is that when you're doing a calculation, write the thing that just has 1 unit first, because I think it makes things nicer. So 3 moles will be our starting point rather than molar mass. Mathematically, it doesn't really make a difference. I just like starting with a single unit rather than 2. Starting with moles, and we're looking for mass. We're very helpfully provided the molar mass. I may choose to do that on some future exams. So 3.00 moles calcium carbonate. Our conversion factor is grams over moles. We want to get to grams, so we're going to put the grams on top. So 100.09 grams per mole. That means the moles ends up on the bottom. And the moles cancel. So MOL cancels MOL. This is usually how you'll see me write it. If you would like to, because some people maybe are confused, like why isn't there a unit that goes along with the grams? Like where's the chemical that goes along with those? I omit it by habit. If you want to include the chemical with both of those, you're welcome to do that, just so that you keep track of like which compound we're talking about with that number. All right, so those calcium carbonates will cancel in no specific order, and I move everything over a little bit to give me some room. So 3 times 100.09. 300.27 grams CaCO3. We would round that down to 300 grams calcium carbonate. Or if writing it that way makes you feel uncomfortable, 3.00 times 10 to the 2 grams CaCO3. Questions about any of that? If it seems like I'm asking for questions more, it's because I am. All right, chromium metal is used for decorative electroplating of car bumpers and other surfaces. That's that real shiny look, that chrome look, chromium. Find the mass of 0.560 moles of chromium. So we are given moles chromium. We need to find mass. What do we use to convert from moles to mass? We use the molar mass. How do we get the molar mass for chromium? we take a look at our periodic table. So we find chromium. Chromium is Cr. It looks like 51.9961 grams per mole, which is the same as grams over moles. So our calculation will set up with moles chromium multiply by our molar mass our moles cancel and grams and chromium both come through. So 29.1 grams of chromium after rounding. All right, here's a slightly longer calculation. A certain reaction produces 2.81 grams of copper 2 hydroxide, CuOH2. Determine the number of moles produced in the reaction. I'm going to let you do this one as an exercise. So give it a shot. And we'll come back together in 2 minutes, 3 minutes. All right, a reaction produces some copper hydroxide. One of the things we're given here is grams of copper hydroxide. We're also, fortunately, given the chemical formula for copper 2 hydroxide. We want to determine moles. Question?
I don't remember, but is the 2 in the Roman numerals, is that having anything to do with the charge, like ions?
Yes, so the 2 in Roman numerals is the charge of the copper. So it's
Right.
copper with a 2 plus. Hydroxide has a 1 minus charge.
So that would that have to do with like the neutrons? Or no? Is this completely?
Charge has to do with protons and electrons. So it's lost 2 electrons to get a 2 positive charge. All right, so we are starting with grams, and we are trying to go to moles. What do we use to go between grams and moles? Molar mass. So we need molar mass of CuOH2, copper 2 hydroxide. So that's a fun little side calculation that we get to do. We've got copper, we've got oxygen, we've got hydrogen. We have 1 copper, 2 oxygens, 2 hydrogens. Copper has a molar mass of 63.55 grams per mole. Oxygen, 15.999 grams per mole. And hydrogen, about 1.008 grams per mole. So we'll multiply 1 and 63.55, 2 and 15.999, and 2 and 1.008. Add those all together, and that will give us our molar mass for copper hydroxide, copper 2 hydroxide. All right, so a whopping 97.564 grams per mole. This lets us actually do the calculation. So we're going to be using this. Starting with 2.81 grams CuOH2. Are we going to multiply or divide by our molar mass? We're going to divide. We need the grams, which goes along with the number, to be in the denominator on the bottom. So we're going to divide by that number. And that will flip the moles up to the top. So our grams cancel, and we'll end up with a small-ish number. .0288 mole CuOH2. Questions about any of that process? Yes?
How do we determine how far we go with past the decimal?
For which number?
For our end result?
So for the end result, we have 3 significant figures in our starting number. So I stopped at 3 significant figures. The next one was a 0, so I just dropped the 0. All right, we can combine this with our Avogadro's number to add another step. make things a little bit more interesting, a little bit more applicable perhaps. So we've learned how to convert between particles and moles, singular units and moles. That's like our dozen to one conversion. And we've also learned our conversion between moles and mass, so we can combine those together. For our particles to moles, that's using Avogadro's number. Our friend 6.022 times 10 to the 23. And moles and mass, we're using molar mass. And we can work this left to right or right to left. So an example of this, how many molecules are in 20 grams of chlorine gas? So we're given that it's chlorine gas. Why do horses need oats for their brown eyes? They need them for clear brown eyes. So, for example, you might get a question sometime in the future that just tells you chlorine gas instead of saying Cl2, and you would be expected to figure out that it's Cl2 and not just Cl. We are told that here, though. The clear of clear brown eyes. Horses need oats for clear brown eyes, Brinkelhoff, H7, whatever method you want. So we're going to be starting with grams Cl2. What can we go to from grams? What unit? Moles. We can go from grams to moles. So we can get to moles of Cl2. What do we need to do that conversion? We need our molar mass. 70.90 grams per mole. Once we're in moles, can we convert to the desired molecules? Can we do moles to molecules? We sure can. What do we need to do that conversion? Avogadro's number. Questions about this setup? All right, so starting with 20.0 grams of Cl2, we have grams. We want to get rid of grams to go to moles, so we're going to divide by our molar mass. That'll put the grams on the bottom. The moles will flip up to the top. So we can see that our grams will cancel out. If you put it in and the units didn't cancel out, that would be a sign that maybe you need to flip it, you need to invert it. This is part of why I write out the units every single time, and I highly recommend that you write the units out every single time. As long as you don't get your units mixed up, you'll be able to see before you put anything into your calculator whether you screwed stuff up. So after this step, we will have moles Cl2 as our units that are left over. That matches with what we wanted to have in our solution map. So we can move on to our second step. In our second step, we're using Avogadro's number. Who remembers what the units are for Avogadro's number.
Atoms.
Could be atoms, molecules, formula units over moles. In this case, it's molecules, singular units in 1 mole. Since moles is on the bottom, we're going to put the big number on top with molecules. And writing a little explainer down here in case you come back and look at it. Another way that we could figure out that the number goes on top is there's a lot of molecules in 1 mole, because our mole is like a crazy large number of molecules. So we would be going from a somewhat reasonable number, 20 over 70, a little bit less than 1, but within the realm of imagination, to an entirely unreasonably large number, 6.022 times 10 to the 23. So our moles cancel, and then we multiply the things on top, divide the things on the bottom, in whichever order you would like to do them. The numbers that come through, or the units that come through rather, will be molecules Cl2. And the number part, 1.698 and some other stuff times 10 to the 23 molecules Cl2. For significant figures, we started with 3. We used molar mass that had 4. We could have gotten more if we needed to. The Avogadro's number that we used also has 4. You can get more if you need to. So the smallest of those is 3. So we'll be rounding the 9 up. So this turns into 1.70 times 10 to the 23 molecules Cl2. Questions?
Do you care if we report it as like in scientific notation with the E or times 10 to the power of?
I would recommend, so there's a question about whether we should use E or 10 to the power of. When you're writing it down, write times 10 to the power of whatever. In your calculator, though, your calculator understands the E's. So if you're happy doing it that way on the calculator, go for it. I think it's a little bit more human, though, to write out the times 10 to the power of whatever. All right, here's one for you to do. Calculate the mass of 2.46 times 10 to the 24 argon atoms. I'll give you 4 minutes. All right. So we are calculating the mass of 2.46 times 10 to the 24 argon atoms. So we're starting with atoms AR going to unit of mass, grams AR. We can convert from atoms to moles and from moles to grams. So we've got a two-step calculation. We're going to be using Avogadro's number for the first step and our molar mass for the second step. So starting with our somewhat ridiculous 2.46 times 10 to the 24 atoms argon. We need to use Avogadro's number. We've got a somewhat ridiculous number. We're going to make that into a much less ridiculous number, dividing by Avogadro's number, which is 10 to the 23, not 10 to the 24. That will have atoms with it, and moles will be the other side of the coin. So our atoms cancel. If you did this stepwise, the number here would be like 4. And then we put in our molar mass. We're going from moles to grams. We find from our periodic table argon number 18, 39.948 for its molar mass. And that has units of grams per mole, so that puts the moles down on the bottom where they can cancel out. Our leftover units are grams argon. So putting that all together, we get 163 grams of argon. Rounded to 3 significant figures. Question?
I'm pretty sure I did the math right because I got the same number, but it's 1.6.
You got 1.63?
Yeah.
My guess would be you put in the wrong numbers for your exponents.
I know some calculators also report the scientific notation like far to the right. That's what my lab partner had a problem with.
Another option would be that your calculator is in scientific notation mode and it's just reporting the scientific notation form. That also happens. All right. Other fun stuff that we can do includes calculating mass percent composition, or as you'll often hear it called mass percent. We have a lab that we'll be doing where we'll calculate the mass percent of oxygen in some compound. So mass percent is the percentage, that element's percentage of the total mass of the compound. So our mass percent of element, just whatever element you want, X, is the mass of that compound, or that sample, not that sample, that element, the mass of that element in some sample of the compound over the total mass. So mass of a part, in this case an element, over the mass of the whole, whole with the W, because voids don't have mass unless they're black cats. And then since it's a percent, we multiply by 100%. Otherwise, it would be a mass fraction. An example of using this formula, we've got a 0.358 grams sample of chromium, and that reacts with oxygen to form 0.523 grams of the metal oxide. So our part, since we're looking for the mass percent of chromium, chromium is going to go on the top in the formula, and the metal oxide mass will go on the bottom. So 0.358 grams of chromium divided by 0.523 grams of the metal oxide. We don't know what the formula is, times 100%. Your mass percent will always be less than 100. Mass percent will always be less than 100%. So 0.358 divided by 0.523, multiply by 100. This comes out to 68.5% chromium. We can use mass percent also as a conversion factor. Which we'll get to. Let's say, for example, the FDA recommends a person not consume more than 50 grams of added sugars per day. If you make 801 grams of brownies from scratch using 422 grams of sugar, what is the mass percent of sugar in the brownies? This was like a rough approximation just based off of like the Ghirardelli brownie mix or whatever brand it was that I had sitting around. I didn't actually make the brownies, I just guessed. So let's we want to stay under 50 grams of added sugars. What we're working towards here is how much brownie can we eat in a day? Because that's a very important question I think that some of us might be asking ourselves from time to time. So we're looking for the mass percent of sugar based on a mass of brownies and a mass of sugar, which is part of brownies. So our mass percent of sugar, we put the part, the thing we care about, on top, 422 grams of sugar. Divide that by the total mass, 801 grams of brownies, and multiply by 100% to put into units of percent. And by the rough approximation here, brownies are 52.7% sugar. Not great for our prospects of getting to eat a lot of brownies, particularly if we want to pair it with ice cream. All right, so we can use mass percent composition as a conversion factor. We can use this to convert between grams of an element and grams of a compound. In this case, we're using sugar in place of the element and brownies in place of the compound. So the mass percent composition of sugar in our brownies was about 52%. And there's a way that we can write this out that makes sense. My brain does this sort of automatically, so my apologies if the explanation isn't superb. Great. So we've got our formula. We're going to have grams, in this case of sugar, on the top over grams of brownies times 100%. If we move the percent over, that will transform this into 0.5269 as our ratio of grams sugar to grams brownies. And we can actually just smoosh those together. 0.5269 grams sugar per every 1 gram of brownies. Alternatively, if you wanted a bigger number, 52.69 grams sugar in 100 grams of brownie. So in this lower bottom right corner, the way that we got this number to transfer over to the grams sugar over grams brownies, we just arbitrarily decided, since it's a ratio, we can just choose one of these. I just decided to make it 1 gram of brownies. So we would have to have 0.5269 for our grams of sugar over 1 brownie, 1 gram brownie. Or you can do it with 100 on the bottom, and then it ends up being the same as the percent up on top. We'll end after this slide. So the goal that we were working towards, what mass of brownie can we eat without exceeding that 50 grams of suggested daily value for added sugar, knowing that our brownies are 52.69% sugar by mass. So we're trying to find grams of brownie from 50 grams sugar. In 100 grams of brownies, we're going to have 52.69 grams of sugar. That's the conversion factor that we came up with previously. In order for the grams sugar to cancel, and for us to get grams of brownies, we need to divide by that number. So we're going to flip it, 52.69 grams sugar on the bottom so that our grams of sugar cancel. And then 100 grams brownie on the top. So 50 times 100 divided by 52.69. We get 94 point, let's call it 89 grams of brownies. It's not clear how many significant figures that 50 has. So we'll just put a number up. So if we were really tracking our intake, we were really trying to stay under this 50 grams of added sugar and we knew we weren't consuming any other added sugar, at the end of the day, maybe we plop down about 95 grams of brownie on our scale, and that's our little treat for staying within our macros. Questions? Great. That'll do it for class. See you next week.